Euclidean Geometry, Proportional Intercepts, Part 1. We're going to have a look at proportional intercept theorem, the proof of which is in this series. What the theorem says is that if a line is drawn parallel to one side of a triangle, then it divides the other two sides proportionally. And this means that AP over PB is equal to AQ over QC. That over that equals that over that. The abbreviation, the reference, prop infin. And it can be extended because this line doesn't have to be between A and BC. It could be above or below. So if we went below, notice we say produced if necessary now the other side. There it is below and there it is above. I want you to watch P and Q as it moves above. You'll notice they swap sides because P is on A, B produced, P is on A, B, so P must be on BA produced. And now all we have to do is look at this one and it follows automatically with those. AP over PB equals AQ over QC. So A to P and P to B, A to Q, Q to C in all cases. But you need only look at this one and it will follow automatically there. We have some other spin-offs from there. AP over AB equals AQ over AC. PB over AB equals QC over AC. And PB over AP equals QC over AQ. All sorts of spin-offs from there, but don't say AP over AQ equals PB over QC, because proportional intercept theorem does not say that. This over that equals this over that. But we could get there using algebra following the proportional intercept statement. Also, please do not talk about PQ over BC with proportional intercept theorem. Proportional intercept theorem does not involve the actual parallel sides at all. Let's have a look at some examples. In the first case, there we are. Now notice this isn't quite correct. It says AD over DB is 3 over 2. And I put 3 and 2, but that could be 6 and 4, 9 and 6. So that is wrong. We'll have to write, to make it a ratio, 3x, 2x. Now it's correct, where we have a variable there. It doesn't have to be x, it can be a, m, anything. So now by proportional intercept theorem, well, not by proportional intercept theorem, just by proportion, if we want to know AD, well, AD is 3/5 of that whole line, 3/5 of 20, giving us 12. That wasn't even in geometry, that's just straight mathematical ratio proportion. Having a look at the second one now. We have to find EC. Now, I'm going to keep emphasizing this. Rather write what you're trying to find first. So EC over, and it'll be EC over AB, AE equals DB over AD. Now we can fill in the measures. Notice I haven't put the x's in because they'd cancel anyway, and that gives us EC is 36 over 5. Having a look at the next one. Once again, I filled in 4x, 3x for the ratio 4, 3, and that's 35. We're asked to find AD, so I'm going to write AD over AB. Seeing that I know AB is equal to AE over AC, following the pattern. AC is 4x plus 3x, which is 7x. So therefore AE over AC will be 4x over 7x, or 4/7, giving us AD is 20. This next one, number 4. We have to find EC. Well, much the same thing. We've got actual measurements there now. We're going to write EC over. So EC over AE equals DB over AD. Slot in the values and we can solve for EC, 33 centimeters. Finally, there are the measurements, and we want to find AC, so we're going to write AC first now. AC over, and AC must go over EC, and it's equal to AB over DB. There are the measurements. Notice AB is 18 plus 12, and that gives us AC. Another example. So here we are, we have to calculate the value of x and y. Well, I'm not going to deal with the whole diagram first, because if you have a look, I can do it with the top half. There we are. And let's ignore this bottom half, because that allows us to find x. Put x over, because once again, as it says, put unknown over known. So we're going to put x over 24, 35 over 21. And that gives us our value of x, which is 40. So now we're going to change triangles. There we are. So we're going to ignore that little line there. This is 56, and that is 24 plus 40. But it will be indicated. So now that's y. There, that's 24 plus 40. This is 21 plus 35, 28. And we're going to put y over once again. And that gives us our value of y. Part 2 is PR over RM equal to QS over SN. The answer is yes. And any line between a number of parallel lines is proportionally divided. But let's have a see why. What I'm going to do is I'm going to join QM. And I now have two triangles with proportional intercept in both. That is parallel to that in the left triangle, and that is parallel to that in the right triangle. So therefore I can say PR over RM is equal to what in this triangle? QT over TM. Now, what is QT over TM equal to in this triangle? Well, follow the parallel line across, QS over SN. Now have a look, we got PR over RM equals QT over TM, which is equal to QS over SN. So we can combine those, and there we have PR over RM equals QS over SN. And there's the reasoning. Let's have a look at a slightly different one. We have to determine the ratio BE over BC. Well, let's isolate. It's quite useful to be able to see which triangles to involve. I can either involve this blue setup here, or I could have gone for these parallel lines here, but the problem is I don't know AD. That's why I'm going here, because I know those two lengths there. So, BE over BC is equal to BF over BD. And that is 3 over 5. Now we need to calculate the length of DA. So we're going to change our triangles now. There we are. And we need DA, so we're going to put DA over. So DA over DB is equal to those ones there, EC over EB. And we know EC over EB is 2x over 3x, which is 2/3. So let's go back and find DA over DB. DA over 5, because DB is 5, 2 plus 3 equals 2 over 3. Which therefore gives us DA is 10 over 3, or 3 1/3. Now we add a little word converse. The converse of the theorem states the opposite. So if a theorem says if this, then that, the converse is if that, then this. Not all theorems, not all converses are true, but proportional intercept theorem converse is. What it says is the line which divides two sides of a triangle proportionally. Now remember that in the proportional intercept theorem we ended up with proportionality and we started with parallel. So this we're going to start with a proportional and end with a parallel. is parallel to the third side of the triangle. And the ones outside also work, but we'll just look at this one for now. So let's have a look at a few examples. Here we need to determine whether PQ is parallel to BC. So every time we're just going to test AP over PB and AQ over QC to see if they're equal. So there, number one, AP over PB, 6 over 4, which gives us 3 over 2. AQ over QC, 9 over 6, also gives us 3 over 2, the same as AP over PB. So therefore this converse works. So therefore PQ is parallel to BC by converse proportional intercept theorem. Number 2, we're going to go for AP over PB again. And it's 5 over 5, which is 1. And then we look at AQ over QC. Well, they're equal, so it's also 1. And therefore equal to AP over PB. So the lines are parallel. Number 3. We have these measurements. That is 8, that is 8, 10 and 10. AP over PB is 8 over 10, which gives us 4/5. AQ over QC is 10 over 8, which gives us 5 over 4, which is not equal to AP over PB. So our conclusion, the lines are not parallel. The final case, there are the measurements, so we're going to put AP over PB, AQ over QC and compare. AP over PB becomes 3 over 2. We cancel 1.5 into both of those. And AQ over QC, 6 over 4, also gives us 3 over 2. So we have AQ over QC equaling AP over PB. Which means the lines are parallel by converse proportional intercept theorem.